Boa tarde a todos. É um prazer hoje receber o nosso visitante, Rafael de Souza. Muito obrigada por aceitar o nosso convite. O Rafael é pesquisador associado em ciências de dados na Universidade de Hertfordshire, na Inglaterra. Trabalhou já nos 3 continentes, Europa, Ásia e Estados Unidos. E, atualmente, ele é pesquisador visitante no IAG, com bolsa FAPESP, e vai ficar com a gente aqui pelo período de 1 ano. Muito obrigada.
Okay, so thanks for the invitation. I think there are some non-Brazilians here, so I'm going to give my talk in English. Just to mention briefly, I'm also associate in North Carolina, and I'm also speaking on behalf of the Cosmic Statistics Initiative. So today's talk is kind of a bit of about philosophy, about astronomy. I'm not going to spend time citing necessarily language, how to code the neural net, and so on. I want to try to provide a bit of the intuition behind. Before I start, may I ask how many of you have used it in any extent neural network? Okay, so some of the concepts I'm going to talk might be a bit new to you. So please stop me anytime. I actually prefer that than just showing all my slides. I think I'm going to be here afterwards, so you can just stop by and talk to me to discuss. Okay, so yeah, today I want to maybe bring some provocative talk about what means, because this is a word that people have been using quite a lot. With different meanings, so that's what I hope try to convey to you first. I think that one of the things I think brings actually this talk I'm giving today is, of course, a change in the landscape in science. This is a very short work we have done recently. We did a simple experience to go to the literature and check how astronomers are citing other fields, because that's a good proxy to see what they are actually consuming, right? What they are reading. So the interesting thing is that when you look for computer science, there is a huge increase. If I recall, it's a 15-fold increase, 15, which means we are reading and citing as a community far more papers, orders of magnitude more papers in computer science than before. And there is a trend in statistics, general relativity and high energy. There was a change as well, I think mostly because of the gravitational discovery, but we are going to focus more in this gradient of increase here, okay? So we are interested in this, which means we are consuming, we are using, and we should discuss. So before we define, or not define, at least to think about what artificial intelligence, the first problem we have is that we actually don't know what intelligence means. And that's actually a huge problem, because every time we say or we try to make a measurement, we need some sort of metric of comparison, right? So I look at a bit the literature, and there are a few different concepts of intelligence that are just historically used, like capacity to achieve a goal, to perform well in tests, solving problems, and then depending what do you mean by problem, which type of problem, and so on. But of course, we know the intelligence is more diverse than that. So we start to think about other dimensions, intelligence in sports, in music, in arts. Ultimately, I think we all kind of agree that intelligence, especially related to humans, is far more complex than any QI test or any test at all can solve. Yet, we have the same issue when we are talking about artificial intelligence, because we still need to define benchmarks. in the moment that you create a model, that you start to talk with GPT or so on, and then you say, wow, this is better than before, you need to base this statement in something, right? So let's try to keep I just want to bring this for you in the beginning to understand everything I'm going to talk afterwards. It's based in some assumptions, right? So again, artificial intelligence is just a word. I don't think anybody here truly believes we already have an intelligent machine, but we are using these words. So let's just try to be on the same page about what we are talking. So there are some concepts that people use. Again, we usually associate what we call machine learning or artificial intelligence to pattern recognition, capability to recognize images, classify galaxies, for instance, or maybe skill acquisition efficiency, maybe, for example, a code that can play chess, Go, or Mario Kart pretty well, or achieve a particular goal. But again, I don't think anybody thinks a computer is actually intelligent just because it can play chess well. Yet, we usually associate this to humans. So just keep this in mind. This is a complex definition, and that it's going to pervade every discussion from now on, more than ever, as the large language models are evolving. Okay, so we need somehow to bring this discussion to our community as well. Of course, apply to our own field. Okay, that said, let's go a bit more practical and talk about a bit history. So everything starts from the idea that it could, this is a neuroscience and philosophical idea back in the day, that it could try to explain the mental states or processes that happen in your brain as a connection or a pattern. Like the concept is that a particular unit doesn't really have meaning or intelligence. A neuron doesn't actually have any intelligence at all. However, as they interact, as you create patterns, or again, mental states, there's some sort of emergency property that brings what you perceive as cleverness. So once you assume that, that's a very crude approximation what a neuron is doing, yet it's extremely powerful. So this is what we call single layer perceptron, which is basically a very basic unit of a neural network. And how should I understand what's happening here? The intuition behind is some sort of logical gate. For instance, it's just a very simple binary problem. Every time you see it's raining, you take an umbrella. If it's not raining, you don't take an umbrella. That's it. That's a single layer perception, right? It's getting input, it's giving you a decision. And what's the magic? How the magic comes out? What's the power of that? Is you can have many types of decisions like that, that ultimately are going to do some kind of weighting, right? Maybe here I want now think about if it's raining or not, if I'm going far away or not, which city I'm living, and so on and so on. So there are different types of inputs that you just sum, do some average, and then you apply what we call activation function, which is nothing more than getting some set of values and giving to you zeros and ones. By zeros and ones being do or do not take action. Okay? So, and if you combine this, you can create highly complex systems. Because just imagine, even if just each one of you is just making one single decision, when you combine in a combinatorial way, you already create a highly complex system. Okay? And that's the idea behind what we call multi-layer perceptron, which is basically a combination, a composition of very simple systems. And again, please, if you have any question, you can stop me anytime, okay? I hope everybody gets everything I'm talking here. So just to give us some quantitative behavior, imagine now that each part of a neural net is just explaining a particular shape. You combine, it's like a Lego, right? You combine one shape, and by doing the composition of these shapes, I can basically model complex functions. And in a similar way as I can do with a Taylor expansion and any expansion, I can reproduce any complex and continuous function as an infinite sum of a single layer perception. So neural networks are universal approximators. That's what we call. That's why they are not necessarily specific for a particular problem. They are just blocks that they can adapt and explain simple things, each of them individually. But when you combine all of them, they can basically approximate, in theory, any curve. So if I can do that, I basically have a language to approximate things in a very abstract way again. And that's why they can be used to so many different applications. Because ultimately, it doesn't really matter much if you have like a text, a chemical structure. I mean, we just saw the Nobel Prize in Chemistry being won by AlphaFold, and sounds, images. As far as you can code this information in some different type of vector, you can approximate whatever this function is and take decision. Okay, so that's the idea. So the difficult part that I'm going to talk a bit more in the next slide is how to decide the projection itself. But once you do that, it basically can do not anything, but a huge amount of things with neural net. So don't think in neural net as a tool to just classify spectra or galaxies or so on. Think them as a language that can represent functions. That's the general interpretation. And by function, I mean any entity that receives input and provides output in a very general way. Okay? And this is just some other applications. I just want to show how they can, can be all be written in the same procedure. Doesn't really matter if you're doing segmentation, classification, or transfer style. This is sound to text, translations, and so on. Because ultimately, you are learning the distribution behind these entities. I'm going to give some examples and go a bit further in particular cases here. But I just want to convey the idea that almost all problems that you see being done, they basically fall in a very similar framework. So as far as you can understand how to phrase your problem in this way, you can immediately apply a neural net to your case. And as astronomers, we are usually interested in few cases that I'm just using a phrase from the data science community, but compression. What I mean by that? If you fit a static profile, if you have a template of libraries to estimate star formation rates, metallicity, and so on, you're doing compression, right? Every time you get raw data and you translate in a physical model in a library for spectrofitting, you are doing compression. Compression means you are translating a complex system in some small atoms of meaning that they can help you to understand, right? So every time you characterize a particular physical system, you are doing compression. Classification, of course. I mean, we love to classify stuff as the biologists. You classify galaxies, you classify spectra, you classify stars, and so on. Surrogate model means you have like that does just highly complex hydrodynamic or magneto-hydrodynamical codes. Some people are looking for ways to speed up this using, for example, neural nets. So usually we might be interested in speed up codes as well. And ultimately we want to discover stuff, right? So you want to find things that we didn't find before. So I'm going to give some examples how we can use these techniques, how we are using these techniques to help in some of these cases. So again, daily, let's say the daily work classic example is discover stuff, right? So one of the works we combined these simple models, nothing complex, but to discover things is in this paper that we have done with the Gaia data to find open cluster. If you don't know what open cluster is, just association of stars that they are gravitational bounds. But from the data perspective, they have similar proper motions, they have similar colors, they follow a particular shape in color magnetism diagrams, and they are physically meaningful because they are born on the same time, so they have similar ages. They can be used as labs for stellar models. So in that case, we had a problem to just run a model in the entire Gaia dataset to look for these objects, and we combine, in this case, just approximators, right? Either neural nets, random forest, doesn't matter. So they can be used to replace or to help, not to replace, but as a tool to be combined with the traditional way how we classify things based in cuts, in color magnitudes or color diagrams. So they are not going to replace the intuition. They're not going to replace how we do science, of course, but they can be useful to speed up the process. And we have been doing similar works using other data sets. That one was we found new structure in the Milky Way by just looking for young stellar objects. Again, young stellar objects are just young stars, baby stars, if you like. They don't go further away from the place they are born. Why? Because they are young, so they don't have time to escape as teenagers, which means they can be used to probe the structure of the star formation regions. Because again, they are close. And we know the spiral arms, it's full of these structures. So by probing them, we actually have a proxy to probe the spiral arm. And again, we use neural nets, random forests, and so on to create a more flexible way to find these objects. And we run again in the cross match between Spitzer, which is the infrared survey, and Gaia. And it helped us basically to find this structure. So again, these are just examples that I understand that at least a few years ago, some part of the community was a bit skeptical about using this technique, which is totally understandable because the interpretability might be a bit tricky. So we don't advocate to use them blindly, but as synergy to how we do science. But I don't think we should just ignore, because they can be extremely useful, and they are going to change. I'm going to talk later in the talk, but I really think they are going to change how we interact with computers in the next decades. So it's highly recommended that, regardless of your field, that we should start to think more and more about how these techniques can be used. Okay? Good. So again, let's talk a bit about the Nobel Prize before I move to other examples. I was part of I looked some groups, and I understand, again, some physicists, they got outraged by, wow, that's not physics, that's computer science, they should not get a Nobel Prize in physics. which I slightly disagree, because actually the intuition behind these models are kind of based in physics and neuroscience. So there are two neural nets that they are the inspiration for the Nobel Prize in physics. And the first one is the Hopfield network. So remember, the single layer perceptron is just some simple thing that takes a decision. The idea of the Hopfield is they assume the brain, how the brain stores memory. This is not a brain model, okay? It's loosely inspired in how they consider the brain to work, which is probably not like that, but still, you know somehow that you have preference. You know that when you see coffee, you already associate some other memories, books, and so on. Just think the amount of information your brain stores, and how amazing is the fact that you can carry far faster than any database we have can carry, right? So you have a super SQL somehow happening in your brain. And the idea is, can we build a neural net that somehow creates memory by just associating things? For example, meaning when I read a book, I think maybe in drinking coffee. When I think about science, I also think in coffee. We all know that astronomers love coffee. Usually may not think about drinking coffee when you run, maybe, but not correlated. So we can create this association, right? If I run, I like to listen music. I usually don't listen music when I read books and so on. So we created these patterns. And technically speaking, these patterns, they are just a matrix, nothing more complex than that. And the matrix stores strength, how much coffee I feel like drinking. If I'm reading, maybe I don't really care if I'm drinking coffee and eating pizza at all, or I really hate the idea, and so on. And then you create these weights, right? Which is basically stored in the matrix. It's nothing magic behind. And once you do that, you just find what we call like the minimal energy structure, because it's like a democracy. Like you try to find a compromise between everything you like for each case, and then the neural net to basically try to find an optimal set of weights in the way that gets like, let's say, what we can write as a minimal energy of the system. And that's how the physics comes in a very intriguing way, because it's exactly the same model used for spin glasses, which I totally don't understand the physics behind, but it's one of the systems that it's inspired by the same principle. And also portfolio optimization. So that's always amazed me, like how different fields, they basically rediscover sometimes the same concept. And they are all basically, mathematically speaking, similar to the Hopfield neural network, okay? So in the way, when you train, even if you fit a line, you can always interpret that as a state of minimal energy of your model. Okay, so that's a direct association to physics. And there are so many others like MC, and Hamiltonian Monte Carlo, and so on. So my point is, you're not giving up physics by looking at computer science at all. And we know how to compress for a long time, but we do that from astronomical perspective. When you do a HR diagram, when you do a color magnitude plot, when you classify galaxies based in magnitudes, luminosity, and so on, the BPT diagram, these are all compressions in a way. The difference, of course, is we feel comfortable with these compressions because they are inspired by a huge amount of intuition, because we do have our brain and our culture. The community is learning how to understand that for a long time. So we kind of can skip directly through these intuitions. nonetheless, there is no there is no commitment from nature to just abide to 2D projections and ones that we can understand. So the difference between neural networks and what we do is that they try to compress in a similar way, but there is still some gap between optimal compression and interpretability from our perspective. But they are not necessarily different from a more, from the nature perspective, because again, there is no reason why we should explain nature events always in 2 or 3 dimensions. Anyway, the simplest type of compression that are more familiar to astronomers, I think it's the principal component analysis. Many of you probably already used that we can use as a replacement for color diagrams. This is just an interesting plot I found. Also, people that study dinosaurs, they do similar work. I also try to explain difference between species by a set of features. And this is just application of PCA in IFU. Steiner was one of the people in IAG that was working in this type of work, research for a long time. So basically, you can create what we call eigenmaps that they explain most of the variance of the data, right? If you don't know what PCA means, PCA is a methodology that tries to find what's most important in your data in terms of the variance. So in the way you are creating, again, some sort of grammar or Legos that you can use as so a combination of these basically recovers the original data set. So every time you find pieces that you can combine together and draw something more complex, that's compression. Okay? No, other direction. So how we jump from that to just highly complex stuff that deep neural nets can do? It's exactly the same. It's just a bit more complicated because they are doing compression as well in something that is, you may see the name called what called manifolds, which is just a curve. And hopefully, if I have a good compression, objects, in this case, puppies, pets, they basically are neighbors in this high dimensional space, and I should find a good representation that keep them neighbors. And that's exactly, for example, what happens in the BPT diagram. You are getting a spectra projecting, and galaxies that they have a similar spectra in the emission lines, they are similar in the BPT, okay? So in a more general way, and I think that might be what the feature expects. And this is one project that I have a collaborator there, the Flat Earth Institute, with Simon's Foundation. They are putting $2 million on this. They want to create something similar to what the GPT does for text, but for astronomy, in which you created this kind of what they call embeddings, which again is just a projection that you can share images, spectra, anything you like. And the hope is there is some dimension here that they will be neighbors. So if it's very powerful if it works properly. Because once you find this, you can basically do inference and translation. In the same way I can get a painting from Picasso, do style transfer and get a Van Gogh style painting. In theory, nothing prevents us to go from the image to the spectra, from the spectra to the image, without actually running any model, because you already have the old model built in your neural net. So that's what might be the feature. Like you just have an interpolation of all sets of possibilities in the way that you could, for instance, just go from one survey to another, look at spectra, and reconstruct the image, and so on. Why? The information is not stored in the spectra. But if you have seen enough spectra, if you have seen enough images, and everything from, you just kind of learn the distribution, underlying distribution of your universe. In theory, of course. Doesn't mean might be possible in a general sense, but might be possible in controlled scenarios. Okay, so that's what they are calling zero-shot prediction. It just means you basically just learn what spectras, images, galaxies, and so on means. So every time you see something new, you already know the values of the property. So yes, that's one of what might be idea for the future, right? With the Astro Foundation, which they don't exist yet, but they might exist in the near future. Astro Foundation model, which is basically creating this abstract data set from which you can basically create surveys, entire mock surveys, for instance, on the fly. It might sound science fiction now, but not many years ago it was science fiction also to win the mastering goal. So we don't know. That might be something to consider. So again, going back to simple things we are doing, nothing like that yet, but just to give you a taste of things that we can do right now. That's work we did with S+ and to find jellyfish galaxies. And the idea is exactly that. We have a subset of jellyfish. We can create some representation, some sort of embedding of these jellyfish galaxies. And jellyfish are just galaxies that they have some sort of disturbance. So they don't look like regular, just to simplify things. But once you have this, I can basically take the list of small objects that I know and just ask, give me the closest image to this object. That's it. That's a very simple question, right? Which is similar to what I'm showing here, right? I can project the images. I can go here. I can ask, give me the neighbors. And then I can get a list of recommended objects. And by just doing this very simple procedure, we can find really good candidates for any galaxy or any type of galaxy or spectra and so on that you are interested. Another work that we have done in a similar fashion was elephant, that was mostly done not by me, but by Bessie, Rupesh, and Liliani, that's here with us. So they did most of the hard work, the young generation. We are just there I was just there basically to prepare coffee for them. And the idea here is to find transients that they don't have a host galaxy, which basically will be a bit different from that one, right? That's a typical transient. You have some dot here, you have a template model, you subtract, you just see the transient. A hostless event, basically the template, I mean, there is nothing there, just the transient. And it might mean that there's actually something there, but it's so faint or so further away that you can't really see them. Or it's a true transient. It doesn't really matter for us if it's a true transient or not right now. What matters is there is nothing here. Why? Because this can be a proxy for energetic events. Because if you are seeing something, but you are not seeing the host, it's a really good proxy for maybe superluminous supernova. And again, same idea. How do you define what's a hostless or a host transient? We can compress the image using a Fourier transform. That's a standard procedure. It's not the machine learning. Any image can be translated can be applied a Fourier transform, and we can estimate the power spectrum of the Fourier transform. And by doing that, we applied a simple argument. If you cannot see something there, but there's something there, if I mix the pixels, there will still be some information that I'm destroying. If I only see noise, if I mix noise, I get noise, right? So there's a gradient of information. If I have a picture of something, and if I mess up, the information change. If I have noise, I mess up, I get noise. So the power spectrum will be different. And by just doing this simple approach, we could find dates for hostless transients. And every week, again, I'm not doing much. They are looking for this. Every week they found dozens of candidates. And again, that's just a simple example that applying this type of procedure enable us to accelerate discovery. And this is being doing under the umbrella of Think, which is one of the LSST brokers, and it was a collaboration with Planck as well. Okay, just for the last part of the talk, I have 20 minutes. So what's the difference between neural nets in general? Why there are so many? Because although they all do kind of the same thing, in the sense they are approximating functions, the cleverness comes from how you do the representation. Nothing prevents us to actually classify images just using a polynomial of order 2. You can do that. It's just going to behave badly. Why? Because it's not capturing spatial information. And that's the idea of the convolutional neural nets, which again could be done with Fourier transforms as well, depending on the situation. So the intuition behind a convolutional neural nets is just you scan your image block by block, and then you do something there. By something means I'm compressing, I'm doing some calculation. It can be an average, can be a kernel application, and so on. So I'm learning correlations between pixels. And we keep doing that. Sorry, you basically learn how your pixels, it's like a language of pixels. Like you learn that a nose usually is close to ears, far away from foot, and so on. So it's like some sort of, you're learning grammars, right? Every time you run this model, they try to learn some grammar. And one of the applications that we use this convolutional neural nets is something that's going to be a problem. I mean, it's a problem already, but it's going to get worse and worse, is to get photometry from blended galaxies. Blended galaxies are not mergers, are just galaxies that, because you're looking further away, they just project in the same position. So every time you try to do photometry, you actually are probably summing up galaxies in your field of view. And the situation is so complex that for LST, for instance, we may have up to 50% of galaxies that are blended, which means half of the galaxies that we do photometry, it's not like a pristine data set. So we applied, again, because you know correlations between pixels and so on, we can learn, for example, how to segment stuff. So we apply something called a UNet that basically gets our original image and splits in 2 masks. And once you do that, you can train your model to go from here to the flux. And by doing that, in comparing to a traditional approach using sex extractor, we can improve the uncertainties or errors of the recovery the flux by order of 4. So again, it's not like it's replacing necessarily, but it actually provides a more flexible way to do things that we already do every day, right? So it's kind of recreating a simple pipeline for source extractor using a neural network. And again, find these concepts. We just released a paper recently called capybara. There's no particular reason for the name, just because I like capybaras. And the idea is the following: if you ever work with data cubes, if you didn't, a data cube is just a set of images. Each slice is like an image of the in a particular wavelength. But because it's a cube, or a spectral cube, we actually, if you look at one particular pixel, there's a spectrum, right? So, which means, so that my idea was the following. Usually, when people do decomposition, boot, disk, and so on, in data cubes, they go to the image. They found the components, and they go back to the cube. And I asked why, because in theory, the information should be stored in the spectrum. Why do I need to go to the images? And I didn't get a good answer, so I decided to try to do this simple experiment. I go to the cubes, I look at the spectrum, I find some sort of, again, embedding simple thing. I see which spectra are similar to each other. I group them, and then I go back. By just doing this simple thing, we can actually, from the cube, not the images, we can find just the compositions here. And if you go to the manga survey, the original web page, you're going to see that when you see these objects here, like foreground stars, they just mask because they cannot run the spectral fitting in these regions. And we don't have this problem because since we are looking only for the spectra, if you have an outlier, it shows up automatically. So that's once you do that, there are two advantages. First, you don't need to do Voronoi binning, which usually is the standard procedure to handle this data set. And second, you can probably fine-tune this package to find supernova, gravitational lens, and so on directly in the cube. And again, this is implemented in Torch, so it's super fast. We can run the entire manga with 10,000 galaxies in 8 hours. As a comparison, if you do a traditional decomposition, it takes 8 hours per cube. So that's how fast it can be done. Just changing the paradigm how we analyze this. And again, I mean, we are not giving up the physics. We are actually taking advantage of the methodology we have. Okay, let me speed up because I think my time is. So to finalize, just a few other examples that we can do. The other model that earned the Nobel Prize is called Boltzmann machines. I don't have time to go to the theory. I just want to let you know that neural nets can also learn distributions, and that's extremely powerful. Okay, this is just a few equations that is telling me there is a distribution of the system, and every time if you look at these equations, it's like a linear regression equation, nothing more. It's a plus b times x. Just there are few dimensions here, so that's just a linear regression. And sigma is what you call a sigmoid function that takes this value and transforms in zeros and one. That's all. But by doing that, I can actually learn distributions. And if I can learn distributions, I can model complex distributions. So every time you try to fit a Gaussian model, a mixture of Gaussians, a mixture of everything, it's interesting to consider that neural nets can be used as distribution approximators. And I think the most famous one is the normalizing flow that we discussed before in the lunch. And in simple terms, if you give a highly complex distribution, it tries to find a series of transformations where distribution is going to look Gaussian. Looks weird, we do all the time. Every time you take a log of your data, you are trying to do the same thing. My data doesn't look Gaussian. I apply a log, it looks Gaussian. But this is just a generalization of that. And it's extremely powerful because this is just an example I did to my class. Let's say I have a distribution like that. If I apply a Gaussian mixture model, it's kind of worked, but not so well. You even find groups that they don't actually exist. So be careful about the bimodality if your data is not really Gaussian, because if you can find actually populations that are not there. But when I apply a normalizing flow, I can approximate my original distribution, and I don't create new modes. So they are, I would say, underused in astronomy yet, but few groups, they are already applying that to do something they call simulation-based inference, which basically, again, if you do MHD, hydrodynamical simulation, that's extremely powerful for you because it can help you to accelerate your simulation and get like full Bayesian analysis in a blink of an eye once you train. Okay, so just to give you possible application. Okay, and finally, what I think is the present feature of AI. There's a lot of stuff to talk. Of course, the time doesn't allow. But I mean, there are things that I think are trends. Quantum machine learning, I didn't talk much. Active inference, I mean, agents, simulated Bayesian inference, foundational models, Bayesian neural nets. They are all fields that are being explored, and I think they will be extremely powerful in the future. In few seconds, what active inference is, everything I told you was based in the fact I have data, I have a model. Active inference goes one step forward and say, look, let's go back how we interact with the world. I'm a baby, I'm learning, I'm interacting, I get feedback, I do something different, I do a mistake, I get feedback, I change. So the environment and my model, they are in that feedback loop. There is no like data and model. You can do both on the same time. So how you translate that to astronomy? Something that we call active inference, active learning. We build this for LSST pipeline to supernova classification. The idea is the following. Usually we assume we have a training set that I have, I don't know, I know things like spectra, photosphere, I have the spectral data. I build a model, I classify. What about if I do follow-ups, meaning I get data that my model asks me to get instead of using my own preconceived experience? It happens that when you do that, it can start from zero, like it just starts from no knowledge at all, and then you just do as a kid. You try, you get random data, you learn, and then you learn how to get data that you need more. What means data I need more? Usually the data about I know less, right? That's how we learn, right? You don't learn reading the same book. So you have a metric that tells, okay, I don't know much about this type of spectrum. So we follow, or we ask for follow-up time for the types of objects that the model know less. And by doing this loop, we can achieve performances far better than traditional approaches. And I just want to remind you that that's exactly how AlphaZero was trained to beat the best players, not by learning from previous games, but by actually learning how to playing against itself. Because then we are not limited by our own preconceived ideas. Okay, anyway, last part, large language models, we all use in a way or another GPT. I'm happy to talk later if you are interested, but just want to convey that they are doing exactly the same thing as everything else, but there's one trick here, is that they know something called positional encoding, which means they not just learn that know good and is a different word, but they know also the order matters, because that's language. So it matters how I talk. And they do so by using things as simple as sines and cosines, because by changing the frequency here, they can encode order. So they have something that we call token, which is basically the word, and they have an index, and the index comes from a transformation using trigonometry. So simple things, but they become very powerful. So it's just a highly complex structure, but it's basically transforming words in vectors, encoding position, passing through a huge amount of matrix dot products. Ultimately, they just have a simple multi-layer perceptron, and they do a prediction. That's why they are not resistant to hallucination, because they don't know what's right and wrong. They just see the frequency, or what's the most likely frequency of words I should expect after asking something. So they don't care if they are lying. Although, it gives something to think. In terms of a data size, GPT-4 was training something around 1 petabyte, which is equivalent to a kid, the same amount of data a kid of 4 years old was exposed in a lifetime. So that's something that makes some people think if you increase the scale, the models are getting smarter. I don't agree with that. I think they are going to get more skilled, not smarter. So there are some approaches that they try to, and again, this brings back what I think might be for us. It's called a retrieved augmented generation. Instead of asking GPT, I have another layer, let's say all possible books I could give in astronomy. And I asked the GPT to go to these books first and only retrieve from that database. So we could combine these models with, for example, a survey in which you train the model to know about your survey only. So it mitigates hallucination drastically. And finally, these models are not intelligent at all, depending how you ask. There's a group, mostly led by François Chollet from Google. They create like a QI test that large language models they have, which is interesting, near zero intelligence, which means they still have some score. So people are, either the benchmark is still bad, because it should be zero, right? We don't think they are thinking. If it's near 0, one day can be higher. But basically, people are working very hard to create benchmarks to beat large language models, so they are going to co-evolve together. Okay, so if you are interested in this type of topic, it's called abstraction reasoning corpus. And yes, I think that's all. So I don't think we have anything close to artificial intelligence in the sense we see in the movies, but surely they are changing how we interact. I have been teaching data science in the past year and a half, and I could see drastically how my students change, how they approach my exams, and especially my homework after GPT evolved. So we can't escape from that, but we can try to somehow harness these tools in our favor. Okay, I think I'm done. Thank you very much.
Thank you, Rafael. We have time for questions.
Hi, Rafael. Thank you for the nice talk. A question about the universality theorem. If you can represent any function by just one layer, why you need deep learning?
First, because it's a layer with an infinite amount of neurons. So, and also there's a problem of it's just compression. Like because there is no, because it's the same question that I could ask. Why I don't just use polynomials? In theory, you can, or even PCA, right? I mean, in theory, you can, any basis, orthogonal basis, you can express anything, but you might just need an infinite amount. We don't just want to, if I spread my representation in a base that is so large that I'm not compressing, it's useless, although it can approximate. So we don't want just something that approximates, we want to compress as much as possible. And that's why we go for nonlinear versions and highly, again, I don't need convolutional neural nets in theory. I could just explain everything with polynomials, but I may need an infinite amount of polynomials, and I may not just be able to run or converge. So it's about finding sparse solutions, not just a representation.
Rafael, very nice talk. And of course, there are zillions of questions. But with regard to training, in order to boost the velocity of integrating MAGD equations, for instance, in numerically, you mentioned the Boltzmann method in this. Can you elaborate a little bit more on this, how it can be done?
Yeah, so I think the difficulty, again, is even if in theory you can approximate, it may not be efficient. So for example, for the case of Navier-Stokes solutions, people have been using Fourier transforms in neural net. So I think the intuition I can give to you is the following. A neural net is just a function. It behaves as a function. And your equations are functions as well, in a way. I mean, not an analytical function, but it's a function. So every block, you have a map, if you want to be more general, that you have something and something else happens. They can enter there. I guess the point is there is no recipe to bring some, what's the optimal architecture to represent, right? But let's say, for example, you have a particular set of equations that you are integrating over time, and then in the same way, and they behave as an autoregressive problem because I have the configuration state A, and I know how to do to state A plus something, right? And that's exactly how, for example, a recurrent neural net works, because I have an equation there that instead of, for example, because the typical neural net will be something that is just G's, and you have activation function, you have a bias, and you have weights, and something like that. For your case, for instance, it wouldn't be anything like that. It would be something more like X, something like G's, against some thing. And of course, and this is plus minus and state. And this part here will be far more complex than a dot product. Because this could be, this is also a function, right, in a way. And this could be replaced by, for instance, a set of convolutions and so on. I think that's the part that's highly complex. But that's your simulation, right? That's the part that's happening. You have a MHD set of equations that are integrating state I and going to state I plus something. So this is the part that you would replace by a neural network. I don't know if it answers the...
Yeah, all right, but we can discuss further later. Thanks, Rafael.
Rafael, my question is somewhat related with the question of Beth. When you discuss Boltzmann neural, I forgot the complete name.
Machines.
Yes, and there is when you start to talk about that, there is a function sigma that I don't know. You show two slides. The second one is a reconstruction.
Yeah, sigma is something like that, which is basically a map that takes any value and projects between 0 and 1. Because if you have a map that projects anything between 0 and 1, you can plug that, for instance, in a Bernoulli distribution or anything. So the transition from numbers to distributions comes from first, you transform any information in a probability. That's what the sigma does.
Okay.
It's just a function that takes anything, projects between 0 and 1. And then you plug this in some distribution.
Okay, this is interesting because it is somewhat related with the second slide. When you show a reconstruction.
The normalizing flows.
Yes, yes.
Yeah, the normalizing flows are a bit more complex, but ultimately, yes, that's a generalization of the Boltzmann machine, but the intuition is similar. Because, again, we do that already when you apply a log function in a data that is skewed, but in log space looks Gaussian. But the difference here is that I'm not using, this is not a log function, that's a function that does the same, but in a general way. Because I cannot just apply a log here, it's not going to solve my problem. But there is always a function that I can apply that's going to make it Gaussian. And you might think, why I care for this? Because we just know how to do things in this space. Like when you do sampling, we all go back to uniform distribution. Like every way to do sampling, it's always the same, similar way. We go to a very simple uniform distribution, then we do sampling from there, and we do the transformation for a particular distribution. So we kind of know how to do that in a traditional way. So this is just making it a bit more general.
But then you show that that slide that you have something that you want to reconstruct, and yes, this one.
Yeah.
And I would like to understand that because you are telling here that if you try to reconstruct the original data using two Gaussian, Gaussian is this one.
Or 3, I don't remember how many, but yeah.
But this normalized flow obtain a better result, but probably use a non-Gaussian model.
It finds a Gaussian, but in a transformed space. In the sense, but yeah, the distribution is more complex. You might think, but why I care for doing this? Remember, we do that many times in astronomy to try to find if there is more than one population looking for bimodality. But if the data is not really Gaussian, you may find spurious bimodality because the Gaussian mixture model overreacts to non-Gaussianity in the way that creates a new mode that it's not there. So that's the point. Yes, I'm using a more complex function here, which is the case, but I'm also preserving just the right amount of modes in my data.
Oh, yes, this is an interesting example for a discussion in the foundations of statistical mechanics that in some situations Gaussian functions should be replaced by non-Gaussian functions. But do you have some example of the opposite, that Gaussian models or a mixture of Gaussian functions may work better than the non-Gaussian
I mean, if the data is actually truly Gaussian, surely the Gaussian will work better. In the same way that if I fit a neural net in a data that should be a straight line, it's nonsensical to do that, right?
Okay, then this depends of the specific case.
Yes.
But then there is some for instance, when you have a complex system, probably a non-Gaussian approach may work better.
I mean, if you don't have high errors, because it is also may overreact to noise, right? So I don't want to say this is better universally, because it's going to model noise as well. So need to be careful. But
More questions?
Thank you, Rafael, for this talk. I'd like to pick your brains on something general. Do you think AI will ever be capable of leading to change in paradigm? I mean in the following sense. Imagine that it's analyzing data from the perihelion advance of Mercury. Will it be able to infer that actually the best description is gravity as space-time curvature instead of improving terms of gravitational potential?
I mean, I can lead to discussion that this is discussion people have been doing largely in the community. I don't know. However, I wouldn't be so. Let me try to give. I mean, I can't say that because I cannot see the field. But what I think it amazes me is not that these diseases are smart. They are not. It's the fact that they are stupid and yet they can outperform us in many tasks. So I think that's the amazing part. It's not really the. So which means either we are not as smart as we think, or there's something around what we need to. Because here, how we do stuff that we like to think that we have creativity. Is it really the case, or we just do smart composition of things? I don't know the answer, but it depending how we phrase things, the answer might be yes or no. Because ultimately, when I do a paper, I'm not creating something so revolutionary. I'm using my state of knowledge and composing, interpolating, using a cultural knowledge, right? So our cleverness is a social cleverness. I mean, if someone drops me in the jungle, I may survive, I don't know, half a day, right? So if you think that way, maybe they are not going to be gods at all, but they might help us to be smarter. In the same way, we all help each other here to be smart. I like to think more in that way, right? Not just being Skynet scenario, but just extending our cleverness. Yeah.
More question? No? Thank you again, Rafael.